What's up, everybody? Today we're going through Chapter 1 of the Hebler Stacks textbook, the homework problems, questions 1-11 through 1-21. So let's get right into this. Question 1-11. Represent each of the following with SI units, so that's something worth noting. Having an appropriate prefix, and that's another thing worth noting. So let's write down A real quick. And I included the SI unit table right here, the metric system. So A is going to be 8,653 milliseconds. So let's take another look at this. SI units. So we have to represent an SI unit. So one of these guys on the table, one of these symbols right here. And then it's going to have an appropriate prefix. So basically what this means is we need to orient the leftmost number one or two places, no more than that, around the decimal. So as you can see, let's just say, for instance, on the first one here, we have this. Okay, we want it like this, or like, let's say this, or even this, something like that. That's what we're looking for. Okay, we want to orient the number. Oh, whoops, excuse me. The decimal is supposed to be right here. We want to orient the number somewhere around the leftmost number, so it's easier to work with. So the first one, let's write this down again, 8,653. And like in questions 1-1 through 1-10, basically you can just replace the symbol here with the multiplier. So we're just going to do that. So the milli symbol, we find that guy over here, m, 10 to the negative 3. So we can just replace that. Then our seconds don't go away, that's our unit. So then we go to the next line down. And now we have to get rid of the 10 to the negative 3, so we can just have it in seconds. Or yes, so we can just have it in seconds. And seconds is the SI unit for time, second. So we want it in seconds, and we want the decimal closer to the left. And conveniently, this does that for us, just like these questions are set up to do. So 10 to the negative 3, that's the same as multiplying or dividing by 1,000, excuse me, or multiplying by 1 over 1,000. And that also moves the decimal to the left 3 places. You can just look up here, and that's how much it moves the decimal, negative 3. So 1, 2, 3. Then we get an answer of 8.653 seconds. Look at that, nice and clean. Then we go down to B. And B, we have, once again, 8368 this time, newtons. So we want to get the decimal closer to the left. Right now it's all the way back here. So I have a very nice proposal. Let's actually get it. Let's move it 3 places again. Let's just move it 3 places right now. So this is our number. Our decimal is right here at the end. So if you move it 3 places to the left, that means we're going up in unit size by a magnitude of 3. So 1 to deca, to hecto, and to kilo. Every unit is equal to another power, or every place the decimal is equal to another power. So we can put the decimal right here. So 1, 2, 3, and then we get kilonewtons. And that's exactly what the answer is. Now our decimal is to the left. It's nice and oriented around our number. We have a nice SI unit here, and everything's happy dandy. Now this number is much easier to work with, and we're going to box our answer because that's the correct thing to do. And finally, we move on to C. So we have 0.893 kilograms. And this one, we're actually still gonna move the decimal. We're gonna make this number not to the thousands, but the hundreds, as you can already predict probably. So we're gonna move the decimal to the right 3 places. That's gonna give us a nice appropriate prefix. We're gonna get this in grams. So let's write this out. 10 to the positive 3 grams. Okay, we want this in grams. So 10 to the positive 3, that's same as multiplying by 1,000, aka moving the decimal to the right 3 times. So 1, 2, 3. And that gives us an answer of 893 grams. Box that, and we're good to go. So this one right here is a little bit questionable. Personally, I think it was in proper form before. I don't know why it really had to be changed, but that was the answer key. And yes, a little bit wonky here, but pretty straightforward on the first two. So moving on, 1-12, evaluate each of the following to 3 significant figures. Okay, that deserves another underline. And express each answer in SI units using an appropriate prefix. So let's get right to it. So A, these take quite a substantial amount of time, just saying. So 684 micrometers divided by 43 milliseconds. So once again, like we did in problem 1-11, we're going to replace the symbols with the multipliers. So we have 684, and we want to replace micro with the symbol here with 10 to the negative 6, because that's what the multiplier is, and leave our meters because that's our unit, our primary base unit here, what it represents. Then we have 43, and then a milli is 10 to the negative third, and then we have our seconds still. So with these problems where we're simplifying to SI units and there's a top and bottom here, we always want to prioritize the bottom. We always want to get this to the middle value right here between deca and deci. We want to get it to its unit, its second, its meter, its kilogram. That's what we want it at. It's Newton. We want it at the middle. We don't want it in mega. We don't want it in giga. We don't want it in micro. We want it like this, like a second. So what we're going to do here is everything's fine and dandy on the bottom except for the 10 to the negative 3. That needs to go, because that's what's representing a milli still. It's still representing a milli right now. Well, it's representing a milli in terms of just seconds. So we want to get this guy to the top. When you move something to a power to the top of a fraction from the denominator, the power itself switches sign. So if this was positive, it'd become a negative up here. And since it's negative, it's going to become a positive. So let me actually write this out one more time so you can really see it. So 684. Then we have our 10 to the negative 6. Then we have our 10 to the third. And then we have our meter. Then the bottom we have our 43 seconds. And now these guys, they're multiplying each other. And powers, when they're multiplying, add. So negative 6 plus 3 equals negative 3. So what we're going to have on the top here, this is so sloppy, I apologize. 684 and then 10 to the negative third meters over our 43 seconds. And then that is going to equal 10 to the negative third, right? That is a millimeter, so don't forget about that. That's very important. So I'm just going to skip right to the answer right now. Once you plug this into your calculator, okay, forget this. We're going to replace that with a milli. Once you plug 684 divided by 43 in your calculator, you're going to get 15.9 millimeters per second. And that is going to give you 3 significant figures, SI units, seconds is the main priority here, in absolute form. Appropriate prefix, looks good to me. Okay, looks good to me. Everything checks out. 15.9, not 100 and or not like 0.0159, okay? It's nothing like that. Then we move on to B. I'm actually going to change my colors real quick because this might get a little messy if I don't. So B, this one's going to be a little longer. Here we have 28 milliseconds. Then we have 0.0458 megameters. And that is all over the magic number of 348 milligrams. So like the first one, we want to get these units into their multipliers. So let's just jump right ahead and do that. So 28 milli 10 to the negative third seconds. And once again, I'm pulling that from the table, the multipliers. And then you can actually write these multipliers too as well, the ones down this column. But that's just, it's going to take a lot of space, if you know what I mean. That's going to be huge. The 10 to the power is much easier to write. 0.0458. And then mega becomes 10 to the positive 6 meters. Then that's all over. This is where you might slip up if you're not too careful. 348, and then kilogram is the SI unit for mass. It's not gram, it's kilogram. So if we're starting all the way at milli, we're going to go 1, 2, 3. 1, 2, 3. We're going up 6. So our prefix is going up by a magnitude of 10 to the 6. Therefore, our number goes down by 10 to the negative 6. They're inversely correlated. So here it's going to be 10 to the negative 6 kilograms. So what we did there is because the unit is a million times larger, the number itself is a million times smaller. So like previously, we want to get this bad boy to the top, right? We got our SI unit on the bottom here. We got kilograms. We want to get 10 to the negative 6 up top. So let's portray that real quick. So 10 to the negative 6 is going to become 10 to the positive 6. That's going to be multiplied by 28. 10 to the negative third seconds multiplied by 0.0458. Hope I have enough room here. 10 to the positive 6 meters all over our nice little friendly bottom now. 348 kilograms. So now we have to get rid of this 10 to the 6. So I've already found out a great spot. Let's just make this seconds. Then we get another SI unit. Cross that out. 10 to the positive third. Once again, 6 added with negative 3 comes out to positive 3. So 10 to the third. And now we have to do something with this. And once again, like you're going to see happen in the following problems, the meter gets the boot. The meter is going to be affected. This can become to the 9th. So let's write this out real quick. Finally, we have 28 seconds because our 10 to the negative third canceled with the 10 to the positive 6. And we have, well, actually, let me rewrite this for you. Let me show you something really quickly with the small space I have. Let's leave this as a 6. Okay, that's going to be a 6 still. This 10 to the positive 3 that we still have here, because I never crossed it out because I'm stupid. This guy, we're actually just going to straight up move the decimal. We're going to multiply this by 1,000, moving the decimal to the right by 3 places, making the number larger, because as multiplying by 1,000 typically does, it makes the number larger. So let's move the decimal. 1, 2, 3. Then we have 45.8 meters to the 6th. This is so much easier to work with. Now we can turn that into mega. So 45.8 megameters. And then that is over our magic number of 348 kilograms. And then that checks out to me. You can see that these multiplied and divided by this is going to equal a nice number oriented around the decimal. Then we just have to make sure to put it in 3 sig figs. So you type that into your calculator. 28 multiplied by 45.8 all over 348. That's going to come out to a clean number of 3.69 megameters times second over kilogram. That is so nice. That's awesome. And then, as you can probably tell for C, I'm gonna have to do some erasing of the entire slide. So we got C, 2.68 millimeters multiplied by 426 megagrams. So for this guy, we're just gonna simplify. Ha ha ha. We're gonna simplify this, and I can already tell you meters, like in the last problem, meters is gonna get the boot, and we're gonna prioritize the kilograms. So 2.68, and then meters, millimeters, that's 10 to the negative third. Once again, we're changing the symbols with the multipliers. And then we're gonna have our 426, and then mega, so we only wanna go from mega to kilo, so that's only a difference of 10 to the positive 3. So we're going to put 10 to the positive 3 because our symbol is going to get smaller, so our number gets larger. Kilograms. And would you look at that? These are going to cancel. So let's cancel these out. So we get 2.68 meters. And I'll show you why I was a little questionable there. And 426 kilograms. Then these are going to multiply, and they're going to come out to be 1140 Okay, meters times kilograms. And the way the answer key does this is why I'm a little delayed on this one. I'm just questioning my own actions. So this is what you typically get. This is probably what you'd end up getting. But as you can see, the decimal's all the way back here, and we want appropriate prefixes. So to move the decimal over, we're going to go 1, 2, 3. And that's going to make the unit smaller because it's going to make the unit larger, because consequently we're making the number smaller by a magnitude of 10 to the third. So if we're making the number smaller by a magnitude of 10 to the third, we're making the unit larger by a magnitude of 10 to the third. Therefore we go 1, 2, 3, and we're at kilo. So 1.140 kilometers multiplied by kilograms. And we're actually going to do this one more time. 1.14 kilometers multiplied by kilograms. That is 3 sig figs. That is oriented around the decimal, and it's in SI units. So there was A, B, and C there. These are some of the hardest ones I feel like in this question set. So don't be too scared, but these were quite intimidating. So moving on, 1-13. The density, mass over volume, of aluminum is 5.26 slugs over feet cubed. Determine its density in SI units. Use an appropriate prefix. So, I mean, keywords here, obviously, we want to take note of this. That's important. SI units and the appropriate prefix, those are all pretty important. So I'm just going to put A anyways. I'm used to that. So we want to find the mass in SI units, and right now we're in some kind of Imperial English BS, so we cannot have that. These suck. I don't even know what a slug is other than an insect. So 5.26 slugs per feet cubed, and we want to convert that into most likely kilograms per meter or something along those lines. So in one slug there are lots of slimy things, but there are also 32.174 pounds. A slug is a unit of force, and a pound is also conveniently a unit of force, so it's just how many of this smaller unit of force are in one of these bigger unit of forces. And for some reason, comes out to a very weird number because the English system is awful. So slugs cancel, and then we want to get kilograms because I'm suspecting we want kilograms as of right now. So we're going to do 2.205 pounds, and that's going to be 1 kilogram. Once again, these are equal to each other, 2.205 pounds and 1 kilogram. The pounds cancel out because I put this one on the bottom because I'm smart. Same as right here, I put the slug on the bottom, so they canceled out, because if I put the slug on the top, this would be slug squared over feet cubed to multiply by pounds, and this would be a mess. So we got our kilograms, that's awesome. So now let's convert our distance. So we got 1 foot is equal to 0.3048 meters, I believe is what it is. Yes, that's what it is. And then we put the other parenthesis, and we cube that because this is cubed. We want to get rid of that cubed. If we just had 1 foot here, this would be squared still, and things would look very bad. So the foot and the cubed cancel, but this number becomes cubed, and the unit here becomes cubed, which is awesome because we want meters cubed. So then you can plug this guy in, and you should come out getting 2710 kilograms per meters cubed. But this is not what the answer key wants, because once again, let's look for an appropriate prefix. Look at the decimal all the way back here, okay? Meters cubed, we're not touching that. That looks great to me. We're not playing with that guy. So we're gonna play with the mass. So real quick, let's up the unit size to downgrade the number size. So if we're at kilo already, let's go up to mega. 10 to the 6th opposed to 10 to the 3rd. So this is going to be 2710 10 to the -3 megagrams per meter cubed. And all I did there was take the difference of the kilogram and the megagram, and we're going to multiply by 10 to the negative third, which is also equal to moving the decimal to the left 3 spaces. 3 spaces. Cross that out. 1, 2, 3. And then we get our final answer of 2.71 megagrams per meter cubed. And I just want to go through that how you would have likely. I wouldn't have seen to convert kilograms to megagrams up here until after the fact, like you probably would have, because the decimal place all the way back here, and we want it within 2 or 3. So there we go. We got it in 1 up the front. So awesome. That one's not too bad. Okay, 1-14. Evaluate each of the following to 3 significant figures and express each answer in SI units using an appropriate prefix. So once again, like past problems, our keywords 3 sig figs, SI units, and appropriate prefix. You can read that anymore. So A, our at symbol, 212 millinewtons squared. So what happens here with the square is not only does the unit get squared, but the number gets squared as well. So let's really dissect this guy. Let me pull out my calculator. We know that if you type 212 squared in your calculator, that comes out to 44944. Very symmetrical number. And then we get our millinewtons, and that's squared. So real quick, we got to convert millinewtons, but hold your horses, because this is a little different. Here, our milli is 10 to the negative third. Our milli is being exponented. I don't know what you want to call it. Our milli is to a power. So basically our power to a power, they multiply. So our negative 3 multiplied by, I'll even write this out. So negative 3. So 2 times negative 3 is going to be negative 6. So instead of our milli being 10 to the negative 3, there's actually 2 of them here because it's newtons squared. So it's going to be 10 to the negative 6. And then we keep the newton squared, because the unit squared, that does not go away. So then for this guy, we're going to move the decimal over a couple times, but not too many times, because once again, we want to orientate the decimal as close to the left number as possible. But we can't really do too much because the newtons are squared, and any movement will be very significant if we change this unit. 'Cause it's going to change if we move this up to kilo. It's all of a sudden going to become 6 times because it's squared still. So we're going to take, instead, we're going to do a little bit different approach. Watch this. So what I did there was I basically factored in, I basically divided by 1,000. I basically multiplied by 1 over 1,000, aka 10 to the negative 3. So let's do that. Let's move this guy, let's move the decimal over 10 to the negative 3, which is 3 spaces. 1, 2, 3. And watch this. 44.944, 10 to the negative 3 newtons squared, and 3 sig figs, so 44.9, 10 to the negative 3 newtons squared. And that's our answer. 44.9, once again I'll say it because it looks pretty bad. 44.9 times 10 to the negative third power multiplied by newtons squared. So then I'm changing the color again because this is going to be bad. So we got B. And B looks like it's going to be a quite big number. So 52,800 milliseconds and all of that squared. So this is a doozy. So 52,800 squared, that's going to yield, what is that going to yield? 27,84,0,0,0. And we'll put some commas in there just to organize this. So 2 billion is what we got. Then our then we got milliseconds, and up here, I'm not gonna go into too much depth. We did it up here. Milli ended up being 10 to the negative 6 because it's squared. It's inside the square here. So 10 to the negative 6, and then our seconds. So awesome. I already know where this one's going. and I hope you see that too. All in seconds is squared as well. So all we're going to do here is factor out the 10 to the negative 6, put it right in this guy. So we're just going to cross that guy out, and we're going to go over 6 places, negative 6 places. 1, 2, 3, 4, 5, 6. That's the same as dividing by a million, because that's what this is. It's basically dividing by a million or multiplying by 1 over a million. That's going to be 27, 87, 84, and our decimal place is going to be right between 1, 2, 3, 4, 5, 6. It's going to be right between the second 7 and the 8. And look at that. But hold up. You might notice this decimal. It needs to be over more. So we're going to keep the seconds. We're going to keep it in SI units because it's nice when it's seconds. It looks very nice. So we're going to move the decimal over to the left another 3. 1, 2, 3. And then we get 2.78784 seconds squared. But actually you don't, because it's actually going to be 10 to the third as well before this. My bad. And this represents moving it back. That's what the number actually is. So right here, this is basically our kilo. It looks like a kilo right now. It's in the proper formatting to be a kilo, but instead of basically using the unit here, hope this doesn't confuse you, we're just going to use the multiplier to keep it in the seconds. Because if we didn't use the multiplier to keep it in seconds, it'd be a kilosecond, and we want it in seconds because this is SI form. So, and if you probably have noticed, this is not 3 sig figs. So 2.79 times 10 to the third seconds squared, and that is our final answer for B. And then once again, I made a mess of this, so we're gonna erase it all. I will still be putting the times for each one. When I erase it, I'll be putting the times for each specific part of the question, so you can just skip to that if you need to. So 548, 10 to the 6th, and all this is to the 1/2 power, and this is a millisecond. So real quick, let's do this out. So we know this guy multiplied by 10 to the 6th is simply going to be 0, 0, 0, because we're moving the decimal to the right. 6 times, that's basically a mega right here. So 0, 0, 0, 0, 0, 0, 0, 0, 0, and that's a square root. To the 1/2 power is also equal to square root. Then we have our millisecond. So we're going to take the square root of this guy. Give me a second here. So we have 548, 0, 0, 0, 0, 0, 0 to the 1/2 power. That's going to give us a nice clean answer of 23,409.4, because why not? And then our milliseconds, we're actually just going to go ahead. This isn't squared or halved or anything. We're just going to go ahead and do this guy right now. So 10 to the negative 3 seconds. And this works out super nice, just like they intended it. Because now look, we have our answer here, right? This is our number. And we have our appropriate, or our SI unit, okay? Now we just need the appropriate prefix, and the 10 to the negative third here works out perfectly. Once again, this is the same as dividing by 1,000 or multiplying by 1 over 1,000, and it's also the same as moving the decimal to the left 3 places, because we're dividing by 1,000. If you divided it by 1,000, you could see how this happens. 1, 2, 3. Then we got our awesome answer, and we're gonna cancel that with the decimal place moving. 23.4 seconds, and look at that. So they're getting longer, as you can tell, but we just gotta keep powering through these questions. That's all it takes. Just keep some powering through. Okay. 1-15. Using the SI system of units, show that equation 1-12 is a dimensionally homogeneous equation which gives F in newtons. So let's pause right now. All we want to do right now, what this is wanting us to do, is use the basically use the SI units in the equation, to prove that it comes out as newtons. So first, let's write down our equation. F equals G multiplied by the first mass over the second mass. This is a Newton's gravitational law question, by the way, in case you didn't know. Then r squared, which is our distance between the two objects squared. So gravitational constant, which has some funky units, mass 1, mass 2 in kilograms, and then our distance in meters, and that all equals a Newton. So let's break this down. So let's break down a Newton first off. We know this is equal to an N. What is an N equal to? A kilogram multiplied by a meter per second squared. So now that we have that, that definitely will make it visually a lot easier. So the gravitational constant, the units for that are pretty crazy. So we got meter cubed over kilograms multiplied by second squared. And once again, we're doing nothing with this. We're just proving that it comes out to equal this. So then we have our mass 1, kilogram. We have our mass 2, kilogram. And that's over our meter, because this is the distance between the two, and that's squared. So meters squared. And I hope you can see where the cancellation's happening. So first off, let's cancel these and actually just put a kilogram squared. So these cancel. And then we just have a meter here. Our kilogram and our kilogram square cancels. So now we're at now we're already at a kilogram per meter or kilogram multiplied by meter per second squared. Look at how that just came out. I didn't even realize it. So if you just flip this over, which is totally fine, basic math, meter per second squared. And look at that. Do they equal? Yes, they do. I just proved his theory. Determine the three significant figures. The gravitational force acting between two spheres that are touching each other, so there's no distance between the radius that's given. The mass of each sphere is 200 kilograms and the radius is 300 millimeters. So that is awesome. We needed all that information pretty much. So let's jump right to it. Let's write down our givens. I'm going to actually even write it here, if I can even write. So we know G, it's pretty long. Might not fit where I just put it. 66.3 or 73, excuse me. I always get that mixed up. Multiplied by 10 to the negative 12 meters cubed per kilogram second squared. So that's our G. M1, do we know M1? Of course we do. Between two spheres that are touching each other, the mass of each sphere is 200 kilograms. That's awesome. That makes our life easy. M1 is 200 and M2 is also 200 kilograms. Awesome. And the radius, the mass of each sphere is 200 kilograms and the radius is 300 millimeters. So we also know the radius of both. And that's not the R. The R is the distance between them. So let's find the distance between them real quick. Let's draw our circles. They're touching each other. And here's the middle points, right? Here's radius 1. Here's radius 2 from this point. We know both are 300 millimeters, so all you have to do is basic addition. And what does that come out to be? 300 plus 300 equals 600 millimeters. And we need that in meters, as I had up here, if you remember. See, meter. I specifically said meter many times. Millimeters. So actually, let's just break this down. 600, 10 to the negative third meters. We have our table here. A milli, 10 to the negative third. And then you multiply by that, or you divide by 1,000, which it's also equal to, and that's going to give you 1, 2, 3. So our R, just our R, not R squared, 0.6 meters. And that looks like all the necessary components to make this happen. So F equals 66.73 times 10 to the negative 12. This part kills me. Meters cubed over kilogram multiplied by second squared multiplied by our M1, M2, 200 kilograms, 200 kilograms, and that is over our R squared, so 0.6 squared, and our meters get squared as well there, making us get a Newton. And all you have to do is plug that in your calculator. So F equals 7.41 times 10 to the negative 6 newtons. Comes out to a lot of decimals if you have a calculator that doesn't do this for some reason. And then we look over here. Oh, excuse me, micro is negative 6, my bad. Micro is negative 6, and we can just substitute that prefix in there as an equal sign. So F equals 7.41 micronewtons. Look at that. That's so nice. And did it say anything about 3 sig figs? No, it didn't. It just came out that way. So there you go. So to recap, we proved that this equals newtons by basically solving for all the micro units inside of this equation. And then we dissected our givens, not too hard. Most of them were pretty abundant. The G you just had to know, it's a constant. The M1 and M2 are the masses given. The R is the summation of the 2 radii of the circles, which comes out to 0.6 meters. And then they were all substituted in properly in the equation for G, M1, M2, and R squared, or R, excuse me, and then they were all, yes, and then their answer came out. So that one's not too bad. 1-16. The Pascal, PA, is actually a very small unit of pressure. To show this, convert 1 Pascal, which equals 1 Newton per meter squared. So a unit of pressure is a force over an area. So a Newton is a force, meter squared, as we all know, is area. And we want to convert that to another force over area, pounds per feet squared. So let's do that real quick, and I'll read the rest of it. So 1 Pascal, right? So we know 1 Pascal is equal to a Newton over a meter squared. Let's put a parentheses around that. We're going to do all kinds of unit conversion action. So first off, I'm going to explain a little something. Everyone knows, like we discussed in the previous problem, 1 Newton equals a kilogram times a mass over a second squared, aka an acceleration. This is an acceleration, and typically it's an acceleration due to gravity. And that's what it is in this case when you're dealing with pressures, is it is an acceleration due to gravity. So if we have this on the top and we want to get this to kilograms, so we can convert kilograms to pounds like I see happening, we want to get rid of the meters per second squared. And we know a Newton is a mass multiplied by the acceleration due to gravity, in this case of pressure. Therefore, it makes sense to divide by these units to cancel them out. That will cancel these units out. And in this scenario, we already know a Newton has been multiplied by 9.81 because it's a unit of pressure. And we know it's been multiplied by mass. So all we're going to do here is erase the 9.81 by dividing by 9.81. We're going to divide it out of the Newton. So basically all we have to do here is 9.81 meters per second, and that's over 1. So all we're going to do is divide by 9.81. Oh, this is squared. Get rid of the acceleration, leaving this as a kilogram. So that's going to cancel with this. That's going to become a kilogram, and this cancels. So now we have our awesome kilogram, and then you just multiply by 1 over 9.81 in the calculator. So we have our kilogram. 1 kilogram is 2.205 pounds. Our kilograms cancel, and now we already have pounds. This is already so easy. So now we just need our length in feet now, which is another super easy conversion. So in 1 foot, there are 0.3048 meters. And we want to square that because this is squared, and that would make sense if we didn't. So then our feet get squared, and the unit gets squared here, which cancels, and the number gets squared. So you plug this into your calculator. 1 over 9.81 multiplied by 2.205 multiplied by 0.3048 squared. And then you get this as your awesome, super fantastic answer. You get 20.9 times 10 to the negative third pound per feet squared. So the way you'll probably get it is 0.020, that's what you're going to get. All I did there was move the decimal to the negative 3 spot, so make the number 1,000 times less, divided by 1,000, 1, 2, 3, and then you get this. And that's what you're probably going to get when you plug this guy in. Or you could get this. It's whatever your calculator spits out. So yes, this is to prove it's a very small unit of pressure, and as we can see here, we know we did it right because this is super small. So on to part 2 of the question. Atomic pressure at sea level is 14.7 pounds per inches squared. Okay, how many pascals is this guy? So how many pascals is this? As you can see, we don't have this in those units, but we're going to convert to those units. I'll show you a super easy way around this. There are 2 ways you can do this. You can take Pascal again, or no. You can take this, you can take our 14.7. You can put this through the entire process plus inches. Again, you can put it through this entire unit conversion process that we just did. Or you can do literally 2 lines of this conversion. It actually is quite simple. Look here. This already equals 1 Pascal, right? This equals 1 Pascal. And if we just convert this to pounds per inches squared, we could use this number and use our instant conversion for how many pounds per inches squared are in 1 Pascal to find the pascals instantly, instead of going through this entire process. So if you don't understand what I'm saying, I will show you real quick. So first off, we need to convert this guy, pounds per feet squared, into pounds per inches squared, because that's what our number is. So let's go ahead and do that. We know 1 foot has 12 inches. Then we cancel the feet. Excuse me. Now we cancel the feet because now the feet are squared. Then we square the bottom here. If you'll excuse me 1 second, I'll find out what this comes out to. So in your calculator, 0.0209 multiplied by 1 divided by 12, and that is squared. Then from that, we're going to get, this is what my calculator spits out, 1.45, and then we'll do one more to figure. We'll do that times 10 to the negative third, or 10 to the negative fourth. That's going to be pounds per inches squared. And that's exactly what we have to have up here for the conversion. So we know in total, the reason we did that is because this equals 1 Pascal. And we want to find this in Pascal. So watch how easy this is going to be. 14.7 pounds per inches squared. So now we're solving the question here. So think about this. We want a Pascal. This is equal to a Pascal. This is the exact same units as this, so they will cancel. How are we going to get them to cancel? Well, we don't want to solve for 1 over Pascal. Okay, we don't want that. We don't want 1 over Pascal. Okay, that's not what we're solving. We're solving for Pascals. So Pascal has to be on the top. It's going to be 1 Pascal. It's going to be equal to this. So watch this. 1.451 times 10 to the negative 4 pounds per inches squared. Now, you might be thinking this is kind of crazy. How is this going to work out? But watch. Pounds are on the top. Pounds are on the bottom. This is the bottom of the top, aka still the bottom. Now, inches are on the bottom here, but inches here are on the bottom of the bottom. Okay? So these ones again cancel out. They really do. Believe me, you can test it. You can ask your calc professor. They really do cancel out. So all we're going to do here is 14.7 divided by 1.451 times 10 to the negative fourth. And that's going to yield us, because we're dividing by a very small number, it's obviously going to be very large. So 101. And it's not going to be exactly this. 000 pascals. And the way the answer key has it is, by the way, this is not how the answer key solved this, but it's a very easy way to solve it, and it works. So I would recommend doing this. We basically made our own unit conversion and applied it to the problem. So here we want this in kilopascals because that's the typical unit for Pascal because it's very small, as we proved. And this is a very large number. The decimal is not oriented around it. So 1, 2, 3. So we moved it 10 to the negative 3. So it's a smaller number now, making the unit size larger by 1, 2, 3. So we go up here, 1, 2, 3, kilo, 101 kPa. And now everything's happy, everyone's happy. We solved the problem, we saved the day. So yes, that's basically what we did. To recap, we took 1 Pascal. We decided we know that a Pascal is a force over a area. We divided the force by its gravitational acceleration, turning it into a kilogram. We then converted kilograms to pounds, and we then converted our length unit of meters into feet through a simple conversion and squaring them both to make area. And then we simplified to come out to pounds over feet squared. From there, we converted pounds per feet squared into pounds per inches squared. So we could use our number given, our atmospheric pressure at sea level. So we could use that instant conversion from this Pascal, this number into pascals using this conversion factor and this number given. And that is what we basically did here. So 1-17. Water has a density of 1.94 slugs per feet squared, or cube, excuse me. What is the density expressed in SI units? Fortunately, this looks super easy. So 1.94 slugs per feet cubed. Awesome. And from previous problems, 1 slug. So we just want this in SI units. So super easy. We've done this in, I think, the second problem. Slugs cancel. Okay, excuse me. I'm getting a little bit ahead of myself. 1 slug is 32.174 pounds. So then we have pounds. And then we want to get the pounds to kilograms because that's a unit. That's an SI unit. So 2.205 pounds in 1 kilogram. Pounds cancel. And then moving on, we have to get rid of the feet cubed and 1 foot. Feet are going to cancel. Hold on. There's 0.30. Excuse me. What was that conversion? 48 meters. And that's gonna be cubed because we want this to be cubed, so we can cancel with the feet cubed on the bottom. And then we have meters cubed and the numbers cubed as well. Let's just cube both. Let's just cube them both in here. So that gives us a nice looking answer of kilograms per meters cubed. Did I cross everything out? Yes, I did. So what we're going to do here in our calculator is multiply 1.94, that's how many slugs we have, by, or how many we had, by 32.174, the conversion factor to pounds. Multiply that by 1 over 2.205, our conversion from pounds to kilograms, and multiply that by 1 over 0.3048 meters cubed. And that is going to give us a very fine answer. Fine like a dime, 999.8 kilograms per meter cubed. And we're not going to stop there. We're not happy there. Because we want this in 3 sig figs. 3 sig figs. And let's just say hypothetically we did this. That's not 3 sig figs, that's 1 sig fig. And if we put a decimal at the end, that's 4 sig figs. So what are we going to do here? We are in quite a pickle. Well, I'll show you what we're going to do. So mega, as we all know, is 10 to the 6. Kilo is 10 to the 3rd. So we're going to do a nice conversion of kilograms to megagrams, and you'll see why in just a second. Because we're going to, that's going to give us 1 point, and then we can just go on 0, 0, because we know the next ones we want in sig figs. So yes, so basically if we up the kilograms to megagrams, where the unit size going up by 10 to the 3, so the number gets multiplied by 10 to the negative 3, aka divided by 1,000, aka whatever. So here we go. We're going to divide by 1,000 because this is a conversion. You're going to see it a little different this time. I'm just doing it because this is 1,000. Super convenient. Cancels equals 1 megagram per meter cubed. And because we want 3 sig figs, 1, 0, 0. Pow. And that's 1-17. This conversion was a little bit sloppy, I admit. So basically you do like this. You do 1,000, 10 to the negative 3, and then you do megagrams. Because our number is going to get 1,000 times smaller because our unit gets 1,000 times larger. That's my explanation. So that's 1-17. I hope that wasn't too bad. Moving on, we have 1-18. Evaluate each of the following to 3 sig figs and express each answer in SI units. So we're going to underline again 3 sig figs, SI units, appropriate prefix. Lego. So A, 354 milligrams, and that's going to be multiplied by 45 kilometers. Geez, this one's going to be quite a couple pages here. 0.0356 kilonewtons. So on the bottom we want newtons, up here we want kilograms, and the meter gets the boot. Just remember, the meter is getting the boot on these. That's how it always works. So 354, and then our milli to killi. So we start here, 1, 2, 3, in between at 0, 1, 2, 3 at kilo. So we're going up by a million from 0.001 to 1,000. That's a million. So because our unit size is going up by a million, our number size is sadly going down by a million. So 10 to the negative third kilograms. And yes, this is going to be 45. So sorry, this is getting scrunched. 10 to the third meters, because we're just going to translate this. All we're going to do here is just the kilogram. We're just going to replace symbol with the multiplier. Man, I can barely read that. So then 0.0356, then the kilo, once again, to the multiplier, newtons. Okay, it's going to get a lot neater down here, guys. Don't worry. So we're going to want to get the 10 to the positive third up top, which is going to become 10 to the negative third. And yes, sadly this is going to result very badly for the rest of the units here. But actually, I just realized we actually don't have to do anything. Let me look at this real quick. These are all in SI form right now. We have kilograms, meters, and newtons. 354. Then 10 to the negative 6 kilograms. Then we have our 45. And then we can actually, let's just tack on those 3 zeros from the 10 to the positive third meters to make you see this. And then this is going to be, we can actually move this over 3 spots because it's 10 to the third, same as multiplying by 1,000. So 1, 2, 3, number gets larger. So 35.6 newtons. And you can see already this is going to come out very nicely. So we can just plug this in right now. These are the units of the answer key. It's going to come out awesome. 0.447 kilograms times meters over newtons. And that is awesome. So that one ended up a lot easier than I thought it would. That one, all we did was convert the milli and the killi and this killi to their original states, their zero states, the newtons, the meters, and the kilograms, and then we just used the multipliers to solve because they were already in proper form. So that's super easy. So B. OB 0.00453 megagrams, so that's going to have to be a lot smaller. Then we have our 201 milliseconds. So if we want SI units, ideally this will be in kilograms and this will be in seconds. So without further ado, actually we're going to do this out here. We're going to be smart. 0.00453 10 to the third kilograms. Smaller unit, larger number. Moves by 10 to the third. and that's going to be multiplied by 201, and the milli is 10 to the negative third seconds. Once again, larger unit, smaller number. And as you can already see, this is going to be awesome. These are going to cancel with each other, and it's going to be a happy day. So these cancel, and then because this is a fairly small number, but this is a fairly large number, they multiply, and we're going to get very close to the decimal. And it's going to be an appropriate prefix, and we're going to get 0.911 kilograms times seconds. And once again, with all these, we want 3 sig figs, so the 0 doesn't count. We don't know what that number is. It's okay. 447. We don't know what that number is. 911. If we were to put another 0, that'd become 4, because now we're implying we know what the next number is. So let's box that, and then we're going to erase it with a sad send off because I'm out of room. So moving on to the final one in 1-18, we have C, 435 meganewtons divided by 23.2 millimeters. So here we're going to want meters on the bottom. We always prioritize the bottom unit. That one has to be its absolute form. So 435, and then we want the mega back into its multiplier, 10 to the third newtons, or 10 to the 6 newtons, excuse me. 23.2, we want the milli back, so 10 to the negative third meters. Once again, I'll show you milli. That's what our symbol was. That's what our multiplier is. Then our newton, our mega, let me find that. Our mega is going to be that multiplier. Awesome. And like before in previous questions, we want the 10 to the negative third up top. When you move a number to its power up top, the power sign changes. So this is going to be a positive 3. If it was a positive, it would be a negative, because the negative is going to be a positive. So awesome. 435, 10 to the 6th, 10 to the 3rd newtons, all over 23.2 meters. And as we know, exponents add when they are multiplied, because they have the same bottom number, so they can be multiplied. So it's going to be it's going to equal 9. And if we look over here, the culprit for a 9 is a giga. So real quick, 435 giganewtons over 23.2 meters. And all you need to do, don't get this confused with a number. That's not a number. All you need to do is plug that bad boy in your calculator. The bottom units in SI form properly. That's all that matters with these, when you can't completely simplify it. So then it's a giganewton per meter. That is a lot of force, actually. That's a ton of force. So that's a ton of force. So 18.8 giganewtons per meter. Awesome. So moving on to 1-19, a concrete column has a diameter of, okay, let's start taking notes. It's important to take notes. Gotta be note taker. 350 millimeters. And a length, so we'll put R, no, we won't put R for our unit of length. We'll put L, 2 meters. Okay, and if the density is this guy, determine the weight of the column in pounds. So I can already tell you what we need to do. We have, this is a column, right? A cylinder, yes, a cylinder. So we need to use the volume equation for a cylinder to cancel out the volume, the density, to cancel out the volume and this density right here, and then we're left with our mass, and then from there we can turn megagrams into pounds. So first off, let's find our volume. So the volume of a cylinder is gonna be pi r squared and then times our length. So V equals volume equals pi. I'll show you the units come out here. So our r squared, that's our diameter, is 350. Let me plug that in real quick. I think it's 175. Yes, 175 on the on the radius, I mean. So our radius is equal to 175 millimeters. And because we want these in meters to make it nice and nice, because this is in meters here, so we need them in meters. Either that or we'd have to convert this. I'm not bantering anymore. So let's do something. Let's do a little showing, not telling. 10 to the negative 3 meters. We replace the milli with 10 to the negative 3 like we can. We just take the multiplier and replace it. Then we have 175 times 10 to the negative 3, aka divided by 1,000. That yields 0.175 meters. Awesome. So that is our radius. So 0.175 meters cubed or squared. So that's meters squared. And then once we multiply by our length, which is 2 meters, that turns into meters cubed. So meters squared multiplied by meters is meters cubed. So once you plug that guy in to your calculator, you get 0.1924 meters cubed. Awesome. That was half the battle. So now we need to take our density, convert it into a mass by multiplying by the volume, and then we'll get our weight, which we'll convert to pounds. So 2.45 megagrams per meters cubed, right? Now watch this. If we multiply by our volume, we can cancel them. Look at that. That's the magic of just knowing one thing has to be on the top, one thing has to be on the bottom. That is so magical. And you put that over 1, and look at that, guys. So basically all we're doing here is we're taking the density equation and we're just rearranging it is essentially what we're doing. So like D equals M over V. So if we want to find just the mass, all we do is look, D times V equals M. And look at that. That's all we're doing. Look, we're just multiplying by the it might look a little weird because I'm doing over 1 and all this bull crap, but all we're doing is multiplying by volume to find the mass. So there we go. And we're just going to do it in one nice step. That's why I'm doing it like this. So then the meters cancel, the meters cubed. Then we want to convert megagram to kilogram because I have no idea how many megagrams are in a pound. I don't want to know. So we know there is in 1 megagram, there are 1,000 kilograms, aka 10 to the 3rd kilograms. And then in kilograms, how many pounds are in a kilogram? So in 1 kilogram, there are 2.205 pounds. Number you should have drilled in your head per kilogram. And what do we want this in? Pounds. Perfect. So our megagrams cancel, our meters cubed already canceled. Megagrams cancel, kilograms cancel. So what you plug it into your calculator is 2.45 multiplied by 0.1924 multiplied by 10 to the 3rd multiplied by 2.205 pounds. And all that gives us, can I get a drum roll please? Can I get a drum roll please? Because I'm going to need one. Should give us 471.44 kilograms. No, it should not give us that. Excuse me. What it should give us what this gives us is 1.04 kips. That's the answer key says, but what you're going to get is this. I'll explain the kips in 1 second. What you're going to get is this 1040 pounds, and there are 1,000 kips in 1 pound. Let's actually just show this out real quick. Tiny little unit conversion. So in 1 pound there are 1,000 pounds in 1 kip. So you divide by 1,000 and then you get your 1.04 kips. And there we go. Look at that. So just to recap, what did we do here? Okay, we used the volume of cylinder equation to find our volume. So, and then we found our radius as well, and we multiplied by the length to find our volume. We multiplied by our volume using the density equation. When we multiplied our volume by density to give us a mass using our density equation. From there, we converted megagrams to kilograms, and from kilograms to pounds, we did that conversion. Then we simply plugged it in our calculator. Came out as pounds, and then we converted it to kips. You didn't have to convert it to kips, that was optional, but it came out to 1,040 pounds. And because the decimal's over here and it doesn't say anywhere up here to convert it to appropriate, an appropriate decimal place, but they did and you can put it in kips if you want. So 1,000 pounds in kip, that's the moral of the story. Okay, so moving on, question 1-20. If a man weighs 155 pounds on Earth, specify A, his mass in slugs. Okay, so let's do each part at a time. Let's not read the entire thing. That's kind of a waste of time. So first off, we're converting pounds to slugs. So pretty easy stuff right here. 155 pounds over 1. That looks like child's handwriting. So how many pounds are in a slug? Well, this is a conversion we know from the past. We've used it. There are 32.174 pounds in one slug. I've never seen a slug that weighs that much. So pounds cancel, and then we get our answer in slugs. That should give us 4.81 slugs after you type that in. So that's our answer to A. These are all quite small and like solutions. His mass in kilograms, so 155 pounds here over 1, and we want that in kilograms. There are 2.205 pounds in 1 kilogram. Top and bottom are equal. Pounds are adjacent, so they cancel, opposite or whatever. And then you're gonna get 70.2 kilograms. And it doesn't say sig figs here anyway. You can anywhere you can go wherever you want sig figs, wherever your professor specifies or whatever you want. And his weight in newtons. So we have his what am I thinking of, his mass. So all we need to do is multiply by gravity, which this man's on Earth, so it's gonna be 9.81. So that's his mass, and then we multiply by gravity to find a newton. So let's actually do this over 1. You can see it. 9.81 meters per second squared. And then I could put, actually, let me do it like this. And then you just multiply out 70.2 multiplied by 9.81. That's going to give you 689 newtons. Because a newton is a kilogram multiplied by a meter per second squared. And as you can see, it is most certainly a meter per second squared. So then you get your newton. 689 of them. Jesus. Then finally D, or not finally, we have another one. So then this man gets on the moon somehow, no idea. And also they did not account for like this space suit and stuff. He would weigh extra because of his space suit. You know what I mean? He wouldn't weigh this anymore. If the man is on the moon, where the acceleration due to gravity is 5.30 feet per second squared. Notice how I didn't put it in meters because I hate them. So now we got to determine his weight in pounds and his mass in kilograms. So I'm not quite sure how the answer key determined this, but I'll show you how I'm going to determine this and how it's the superior way. So first off, let's convert the 5.3 feet per second squared into meters per second squared, something not so stupid. So 5.3 feet per second squared, we want to convert that to meters. So in 1 foot, there are 0.3048 meters. So all we're going to do here is multiply 5.3 by 0.3048. Then we're going to get our meters per second because our feet cancel. And we just left meters on top, seconds on the bottom. That's going to give us 1. Oh, excuse me, I got to do it again. Multiply by 0.304, 1.61 or 62. Let's do 62 meters per second squared. Okay, awesome. Now, what do we know about the acceleration on Earth? Well, we know it's 9.81 meters per second squared. Moon, Earth. So things weigh Earth. So things weigh much more on Earth because the acceleration's greater. Things weigh much less on the moon because, well, it's like a fourth. So we want to find his weight in pounds. I say we go about this quite simply. So let's do his pounds out, right? 155 pounds over 1. Let's make this super easy. Let's make a quick little ratio. I'm going to quote this, the Earth to Moon acceleration ratio. So what we're going to do here is basically I'll show you and then explain. Now you make a ratio, the units have to cancel, and in this case it's awesome because they have to. So I have the moon's acceleration on the top and I have the Earth's acceleration on the bottom. We know the moon's is smaller than the Earth's. Okay, you can not only assume that, but you know that by these numbers. The Earth's acceleration is larger, meaning things are going to weigh more. The moon's is less, meaning things are going to weigh less. So this guy should weigh less. That makes a logical sense. So if I was to put 9.81 on the top of this ratio, right? This is any old ratio, okay? I'm sure we all know how to set ratios and proportions by now. 9.81, if I was to put that on the top and divide by 1.62, I'd get something along the lines of 4, okay? This man's not going to weigh 4 times as heavy. He's not going to weigh 4 times as much, you know what I mean? So it's more logical. It's the only way to put 1.62 on top and 9.81 on the bottom. So these are going to divide, and they're going to create a ratio between both the gravities. And that proportion, the ratio between them, is going to multiply by 155 and give us the correct answer. It's basically going to take into account it's going to take into account this number divided by that, which is going to get us how many of the moons fit in the Earth's. And it's going to be a fraction of them because this guy's going to weigh a lot less. And that's going to give us for an answer 25.5 pounds. And I know that one might have been confusing, but if you happen to stumble across the actual answer key online, I think you're going to find that's going to be much more confusing. So this actually makes sense, and the units cancel, and we're left with pounds still, and we get a much smaller number. Much smaller number, 6 times as smallish. And then we go to E, our final one. His mass in kilograms. Okay, don't let this fool you. Don't be stupid, okay? Mass is constant. Mass is always mass, okay? Mass is not newtons, and it's not pounds. It's not a force, okay? Mass is always there. So if this man weighed 155 pounds, that was his mass. Pounds are a force and a mass. I hope I'm getting this across right. Pounds are a force and a mass. So in this case, it's a mass because we're using kilograms. So it's a mass, and we find its mass in kilograms. Mass is a constant measurement. It's not a measurement due to gravity, unlike newtons and pounds in some scenarios. Mass is a constant. So finally, for E, his mass in kilograms is simply 70.2 kilograms. Hope you saw that coming. We're going to box that. We're going to box 25.5 pounds. And that's the answer for this. So to recap, A, all we did was use the conversion from pounds to slugs, the forces, and we get that many slugs. B, we just used conversion from pounds to kilograms, and we came out with kilograms. And these are both correct. Obviously, all these are correct. 70.2 kilograms for C, and what we did there was we multiplied by gravity to give us newtons, like we always have. Weight, basically finding his weight. Whenever you see weight, that always means 9.81 and kilograms or pounds. It's a force. Then for D, finally, we all we did here was convert feet to meters per second squared. Found the acceleration due to gravity on the moon in the metric prefix. Used a proportion between the moon and the Earth. So we're starting from the moon, it's on top, and we know the Earth's as well, and we divided by the Earth's to come out with a certain number that's going to give us the amount of pounds this man weighs on the moon. And then finally, what we did for E was we know mass is a constant over any surface. It doesn't matter the gravity, it doesn't matter if it's zero gravity or all the gravity. Mass is a constant, therefore it's still the same as on Earth. So finally, 1-21. This is the last question of this chapter. Thank God. 2 particles have a mass of 8 kilograms. Okay. So M1 This is Newton's gravitational law again. So M1 equals 8 kilograms. M2 equals, it says 12 kilograms respectively. Okay, if they are 800 millimeters apart, so that's our R. We know our R has to be, let me write down the equation real quick. F equals G multiplied by M1 times M2 all over R squared. So our R has to be in meters, excuse me. So we're going to take our 800. Instead of writing millimeters, we're going to write 10 to the negative third meters. We're just going to look down here. We're going to take the symbol and just replace it with its multiplier. So that's exactly what we did. And 10 to the negative third, multiplying by that, is the same as dividing by 1,000. And everyone knows, divide 800 by 1,000, and guess what you get? R is equal to 0.800 meters, 0.8. And then G is a constant. It's always there. And our G, our magical G, is going to be 66.73 times 10 to the negative 12 meters cubed per kilogram times second squared. I don't know why Mr. Sir Isaac Newton was so important when he couldn't even make a simple unit here. Okay, so we're going to find the force of gravity acting between these two bad boys. I can already tell you, first off, because I've looked at the answer key, and second off, because these masses are so gosh darn small, that this number is going to be so gosh darn small, because this is applied on a cosmic scale, and here we're basically taking two bowling balls and finding the gravitational attraction between them. So if you expect this to be a large number, then I'm so sorry to rain on your parade, but it's going to be microscopic. So we're going to multiply that by our mass 1, which is 8 kilograms respectively. Multiply that by 12 kilograms respectively. And that's going to be divided by our distance between the two particles squared. So in other words, 0.8 meters. And that guy's squared. To prove the units cancel to a Newton, look at this. That's a kilogram. So that cancels, left with kilogram. That cancels, and we're left with a Newton is a kilogram times meters per second squared, kilogram times meter per second squared. Look at that. And then you're going to get for your answer, once you plug in 66.73 multiplied by 10 to the negative 12 multiplied by 8 times 12 all over 0.8 squared. Once you multiply by that, your final answer is going to come out to be 10.0 times 10 to the negative 9th newtons. Now you might be thinking that's pretty small because, well, it is pretty small. And watch when we this only gets better. So we're going to convert it into its symbol now. So 10.0, and then we go negative 9 is all the way down here. We're at nano now. We're basically not even on the charts anymore. Don't look at these. These aren't on the charts either. So we're 10 to the negative 9 is a nano. So we're just going to put nano Newton. Gets a very small n because it's very small. 10.0 nanonewtons. Compare this result with the weight of each particle. So we know this is a super small force. So let's find the forces. Let's find the force of gravity acting on them, of the Earth. So the first one, 8 kilograms. So the force of each particle. So the weight. So the weight of one is 8 kilograms multiplied by 9.81 meters per second squared. And when you plug that doohickey in, you're going to get 78.5 newtons. And then for our weight 2, 12 kilograms multiplied by 9.81 meters per second squared. That's going to give us 118 newtons. So look at all this, okay? Let's take a look at this. So the Earth is exerting this much force on these guys. And as we know, their centroid and the Earth's centroid are very far apart. These guys are literally right next to each other, 800 millimeters apart. almost 1 meter. They're very close to each other, and they're only exerting 10 nanonewtons. That is insane. Okay, that's what is that? 0.01 micronewtons. 0.01 micronewtons. So yes, this is very small compared to the weights. That's what it wanted to get at with this. That the force. So thank you all for watching. I hope you like and subscribe. It would be very appreciated. Comment. Let me know what I'm doing right. Let me know what I'm doing wrong. So thank you. Hope you have an awesome day, and I'll see you next time.